So now that we have a sense of what linear equations look like, and linear equations, broadly speaking, are going to be the objects of study that we're going to look at in linear algebra, now let's get down to nuts and bolts a little bit. So how do we actually solve linear equations? And that's kind of a bigger question than we're going to be able to do justice to just in this video. But what I want to focus on right now is really the nutsy boltsy stuff. Really just what is a strategy if we're given a system of linear equations. And for right now, for this example, we're going to look at a system that has 3 equations in it. So we'll call those equation 1, equation 2, equation 3. As well as 3 variables that participate in those equations. We're going to call them x, y, and z just for convenience. We could call them x1, x2, x3, but I like x, y, and z. So we're going to focus in this video on a strategy for solving equations like this one and begin to think about taking a look at a bigger meaning out of the results of that process. So the strategy we're going to apply is a strategy that's called the application of row operations, sometimes called elementary row operations, sometimes called Gaussian elimination or Gaussian reduction or Gauss-Jordan elimination. It goes by a lot of different names, but the basic steps in it are all the same. So what are we hoping to do in this at the end of the day? Well, the first thing that we can observe is that because if we buy into this idea that what makes linear equations linear is the fact that the only thing that we've done to the variables is multiply them by constants and added or subtracted them together, then the only thing that really matters about the form of these 3 equations are the numbers, the coefficients that are sitting in front of the variables, as well as the right-hand sides of the equation. So the numbers surrounding the x's, y's, and z's are going to determine everything that we do, and the x's, y's, and z's themselves are just going to kind of come along for the ride. So what we'll do is take all of that important information out of this system and write it in what we call an augmented matrix form. So this is the first meeting that we'll have with a matrix in linear algebra. And so for now, for the near future, we're going to think of matrix as just a convenient bookkeeping tactic, right? It's just a convenient way for us to keep track of the various numbers that go into making this system of linear equations what it is. So the first equation in here becomes the first row, 2, 4, -2, and then 16 on the right-hand side. And we'll put this vertical bar here to just give us a visual cue that what comes to the right of it are the right-hand sides of my equations, and what comes to the left of it are the coefficients of my variables x, y, and z. So each equation in my original system becomes a row in this augmented matrix, and each of my variables that I'm trying to solve for becomes one of the columns to the left side of this augmentation bar over here. You'll also notice that I've left a space here blank. And I'm kind of being naive about that for the moment. I left it blank because there was no x participating in this third equation. If I wanted to, I could have written in here 0x and then placed a 0 here in my augmented matrix. But very often when we do linear algebra, when we have a 0 inside of a matrix, we tend to like to create zeros in our matrices and never to destroy them. So once we get a 0, we like that 0 to remain for the rest of time. So very often, we'll just leave that space blank as a visual reminder to ourselves that we don't want there to be a specific quantity there. We want that 0 to remain 0. So I'm going to use that convention in this video, but feel free in your own work to use the 0 there if it helps you to remember what's going on. So our first skill here is just to translate in between the system of equations form and the augmented matrix form for a linear system. Okay, so let's take a moment and think about what our ultimate goal is. If I'm trying to solve an equation, and this is true for any equation in algebra, what I'm really trying to do is do some algebraic operations that will unwrap my unknown quantities from the arithmetic that surrounds them. So I want to get my unknowns, my x's, my y's, and my z's, I need to disentangle them from all the algebra that's happening around them in this system, and hopefully, if we can, get them by themselves. What we'd like to know is, when we're solving a system of equations, what is the value that x takes? What is the value that y takes? What is the value that z takes? Is there a specific choice of x, y, and z that will solve all 3 of these equations at the same time? Or is a solution not possible? Or might there be more than one choice of x, y, and z that satisfy all 3 of these equations? Those are the kinds of questions we want to begin to ask and to answer. And so ultimately, with our eyes on the prize, we want to get an understanding of what x is, what y is, and what z is that's not intertwined with the other variables. So we want x by itself, y by itself, z by itself. So ultimately what we're going to try to do is to take our original augmented matrix and do some stuff to it, some legal stuff, we want to do some stuff to it which was not going to change the solution of the associated system, but which will try and disentangle the x's, y's, and z's from each other, so that we get down to an augmented matrix form that hopefully only has a 1 in the x place on the first row, a 1 in the y place on the second row, a 1 in the z place on the third row, and no other non-zero entries sitting inside of my matrix. So what I want to do, if I can, is get it down to a form that looks like this. And then the numbers which are on the right-hand side of my augmentation bar, those are going to be the values of x, y, and z in my solution, if those specific values happen to exist. So that's the goal. And so what the first thing that does for me is it kind of enshrines these ones that are sitting here in this goal of mine. It enshrines those positions inside of my augmented matrix as being special positions. We call those positions the diagonal of my matrix. And in any matrix that we write down the whole semester, what we mean by the diagonal is it's the set of entries that begins with the first row, first column. So the top leftmost entry in the whole matrix, and then it continues down one step at a time. So this entry, that entry, that entry, and then at that point we stop. So the diagonal consists of these three positions in my augmented matrix, and I'm going to circle or highlight those right now because those are going to be super important for me. Now in my strategy for trying to get me closer to this solution, what I'm going to choose as my strategy is I want a strategy that's going to wipe out, first of all of the non-zero entries that lie underneath this diagonal. So in our example, that's this -1 and this +3. If I can do something to this augmented matrix that wipes out those entries, makes them 0, then that's going to reduce the amount by which x, y, and z are intertwined in my system, and hopefully will let me solve for x, y, and z. So the first thing we're going to do, then, is we're going to set a target. We're going to choose an entry that we want to try and wipe out. And the best way to be strategic about this is to look below the diagonal, again at these two entries, and select the top leftmost entry, which is non-zero. So in my first column, for example, below the diagonal, I have one entry here that is 0, but above it is an entry which is not 0. And that, therefore, is the top leftmost non-zero entry below the diagonal, and that's going to serve as my first target, the first number that I want to zero out in my augmented matrix. So what we want to do now is apply some strategies that are going to turn that -1 into a 0, and this is important, without changing the set of solutions of this system of equations. So that puts some pretty tight restrictions on us. We can't just do whatever we want to the entries that are in this augmented matrix, because these entries mean something specific. They correspond to a set of 3 equations whose solutions must be the same as the solutions of anything that we get afterwards in order for our algebra to be meaningful at all. That is, after all, what happens when we solve an equation in algebra. We replace it with another equation which is hopefully simpler, but which has all the same solutions as the first one. And so the restrictions that puts on us are as follows. If I want to zero out this -1, there are really only 3 things, and we're going to talk about 2 of them in this video, that I'm going to be allowed to do. The first is I'm going to be allowed to multiply any of the rows of this augmented matrix by a constant all the way across. What am I doing there, after all? It's the same as if I had taken one of my equations and just multiplied both sides of this equation by a constant. And as long as that constant is non-zero, which, again, I forgot to mention down here, I should probably put that in the notes. As long as I multiply by a non-zero constant on both sides of an equation, the new equation that I get has all the same solutions as the old. And so that should be something that's legal for us to do. The second fundamental type of thing we can do is to add 2 rows together. So this was an example we saw in the previous video when we were working a little bit with algebra, is that if I have 2 equations which are both true, and I add their left-hand sides together, and I add their right-hand sides together, I'm going to get a new equation which is also therefore true, because the original equations were also true. And because that process is also reversible, I could also subtract it back out if I wanted to. That also allows me to replace any of the equations in this system with that sum if I want to. So this is our second move. I can add 2 rows together and replace one of those rows by the sum that I get. And I have not changed the solutions of the system. Now, the hard part about this is choosing those steps in a way that's going to always lead us closer to our goal. It's going to give us a simpler, less intertwined system of linear equations, where x, y, and z are standing more on their own than they were before. And so that's where the strategy is going to come in handy. And that strategy tells me the first number I'm going to try to knock out is this -1. And I'm going to do so without taking any zeros that I have below or above my diagonal, without ruining any of the zeros that I have below my diagonal. And so that's going to lead me to, when I'm working below the diagonal, to try and work with the rows that are above the entry that I'm trying to zero out. So if I'm trying to zero out this -1, chances are I'm going to do so by using the row that's above it. And in particular, because I'm adding rows together, I'm multiplying rows by constants, I'm never going to be able to get together a coefficient of an x with a coefficient of a z, for example, because they're not like terms. And so the only choice for a number that's going to zero out my -1, which is the coefficient of x in my second equation, is a coefficient of x from another equation. And the only option here that's above it is the 2 that's sitting here in row 1. So the goal here is going to be to somehow use this 2 to knock out this -1. In order to do that, I'm going to use a two-step process. The first step is I want to cut this 2 down to size. I'm going to cut it down so that it's equal to 1 here instead, so that then, if I add that to -1, I'll be able to zero out this entry. So that's why my first choice here is I'm going to multiply this first row by the constant 1/2. That's going to turn this 2 into a 1 and make it easier to use to cancel out that -1. So I'll multiply that first row by 1/2. My new first row becomes 1, 2, -1, and then on the right side of the augmentation bar, 8. Notice again that that's the same as if I had just multiplied both sides of equation number 1 by the number 1/2. I would have gotten 1x plus 2y minus 1z equals 8. And that's indeed what this row here is representing. All right, so that works. And now I'm set up to zero out this -1 by adding these two rows together. Add the first row and the second row together. When I do that, the sum is no longer going to have any x's in it. This is often called, when you first learn about solving linear systems, the method of elimination. We're able to eliminate the x when I add these two rows together because the coefficients of the x's that I have now are equal and opposite. So when I add these two together, the sum is going to have a 0 in that first column, 1 plus -1. And that's indeed exactly what we wanted to accomplish by this set of steps. So we've zeroed out the entry that we were trying to zero out. This is great. It means that we're making progress, getting closer to this goal. But of course, I can't just zero out this x without also adding together the coefficients of the y's, the z's, and the right-hand sides. So I have to add the 2 plus the -7 to get -5. -1 plus 2 is going to give me +1. 8 plus -27 gives me -19. So what I have now is a new system of 3 equations in 3 variables. But there's slightly less intertwining between x, y, and z, because now the only place that the variable x appears is in the first row. And the second and third rows only have y's and z's in them. So we've made some progress. We've gotten closer to disentangling our x's, y's, and z's and discovering the solution of the system. That's great. How do we get closer still? Well, all we have to do is repeat the 2 steps that we just did. Go back to the well, find the top leftmost non-zero entry below the diagonal of my new system, which has the same solutions as my old, and repeat the process. Fortunately for us, there's not much choice here. The only remaining non-zero entry below the diagonal is this +3. And that +3, therefore, is going to be my next target. If I want to zero it out, I have 2 choices for which rows to use. I could try to zero it out using row 1. The problem with that is that if I were to add some multiple of row 1 to row 3, I would be adding some multiple of this 1 to this hallowed 0 entry in the first column, and I don't want to do that. Once I've got a 0 in this process, I want to keep that 0 as long as possible. So instead of using row 1 as my tool to zero out this 3, I'm going to use row 2 instead, because row 2 has this safe 0 here in the first column, which means that no matter how many multiples of row 2 I add to row 3, I'm never going to destroy this 0 that I have here in the first position. So I'm going to use this -5 in row 2 as my tool to get rid of the +3 in row 3. All right, so what multiplication and addition do I need to do to accomplish that? Well, again, in the method of elimination, we want the coefficients of my variable to be equal and opposite, so that when I add them together, we get a 0, where we want there to be a 0. -5 and 3 are not yet equal and opposite, but they can be if I multiply the second row by 3, and I multiply the third row by 5. Right? So multiply each by the other. It's a quick and dirty way to find a common multiple, remember. It's just like finding a common denominator for a set of fractions, right? So if I multiply the second row by 3 and the third row by 5, then These coefficients in the boxes here are going to be negative 15 and positive 15, equal and opposite, which is exactly what we want. But then the other coefficients on those rows are also changing. Note that the zeros are not changing, which is important, but the non-zero entries are. So now we've got negative 15, 3, negative 57, and 15, negative 30, negative 105. But since the coefficients of the y's in row 2 and 3 are now equal and opposite, if I add those rows together, I can eliminate the y. In other words, zero out that entry that I'm trying to zero out, which is exactly what we're trying to do to make more progress. When I do that, adding negative 15 to positive 15, I also need to add 3 to negative 30 and negative 57 to negative 105. So my last row becomes 0, which was always there, a new 0, which we just won, negative 27z equals negative 162. And now all of the entries underneath my diagonal are 0. That's great. That means we've made a ton of progress. In fact, at that point, we've just discovered what's sometimes called the row echelon form of this matrix. All of my entries below the diagonal are now zeros. And we have, therefore, enough information now to determine a solution for this system by a process that we call back substitution. It's called back substitution because we start from the bottom equation and use that bottom equation to discover a value for the only variable which is left in that equation, namely z. Negative 27z equals negative 162. And once we have a value for z, we can then back substitute that z into the previous equations and eliminate the z from the first two equations, solve for x and y. Let's take a look at what that looks like. To do that, we're going to go cross back over the river from augmented matrix form back to equation form. If I do that, my new system is 1x plus 2y minus 1z equals 8, negative 15y plus 3z equals negative 57, negative 27z equals negative 162. And back substitution means let's solve for the one variable which we now know exactly how to solve for because it's been completely disentangled from the others, the z. The third equation, negative 27z equals negative 162. If I divide both sides by negative 27, I get a nice number, it turns out. Z equals 6. Kind of fortunate. In general, linear systems tend to have fractions as their rational numbers as their solutions, even when their original coefficients were integers. But this system happens to be set up in a nice way. So z equals 6. And the back substitution part is then that we're going to use that z equals 6, plug it into the second equation for z, and therefore in the second equation, I only have y left as my unknown. Negative 15y plus 18 equals negative 57. Subtract that 18 from both sides. Divide by negative 15, we find out that y is equal to 5. I can then back substitute both the y and the z that I just found into the first equation to leave me with only one unknown, namely x, in the first equation. 1x plus 2 times 5 minus 1 times 6 is equal to 8. 2 times 5 minus 1 times 6, that's 4, so x plus 4 equals 8. Subtract the 4, x is equal to 4. So we've just discovered, after this back substitution, that if x is equal to 4, y is equal to 5, and z is equal to 6, then this system will be satisfied. But this system is equivalent, row equivalent, to the original system that we started with, and therefore x equals 4, y equals 5, z equals 6 also solves our original system as well. So this is great. What we have, geometrically, if we just take a moment to pause and think about what this actually looks like, what this was a system of three equations, each of which, of these three equations, defines a plane inside of 3 dimensions. So if we think about what linear equations in 3 variables look like, they look like planes, flat surfaces like pieces of paper that extend infinitely far inside of xyz space. And each of these 3 equations describes one such plane. And when I take any 2 of those planes and I intersect them with one another, their intersection is going to be a line, as long as the 2 planes are not parallel to one another. And if I therefore take all of the pairwise intersections of these 3, I'm going to get 3 lines that hopefully come together at a single point. And in this case, that happens. So the 3 equations which describe my 3 planes here happen to meet at a single point, and that point was the point x equals 4, y equals 5, z equals 6. So we have a unique solution for the system, is what we would say. It's consistent, it has a solution, and that solution is unique. There's only one combination of x, y, and z that make all 3 of these equations satisfied, namely x equals 4, y equals 5, z equals 6. But as we'll find out as we go on into next week, that doesn't always happen that way. Not every linear system of equations we can write down has a solution at all. Some of them are what we call inconsistent. There's no x, y, or z in the universe which can make all three equations satisfy, for example. But worse than that, maybe, is that even some systems which are consistent, which do have a solution, will have more than one solution. And in fact, we can prove that a linear equation that has more than one solution necessarily will always have infinitely many solutions. That's a bridge that we're going to cross as we go into next week. But to wrap this up, let's take a step back from the process that we just did, applying a strategy to row reduce a matrix far enough that we can discover its row echelon form, all zeros below the diagonal, and then use back substitution to find a solution for the system. Let's work that backwards and figure out exactly what this solution at the end of the day is telling us. In back substitution, what we did first is we found a value for z. Right? We found a value for this variable at the bottom row of my linear system. And once I found that value, which happened to be a unique value, there's only one value of z that's possible to make this as a consistent system, that was z equals 6. But then we used that z to determine a value for y. And because the value for z was unique, the value that we got for y was also unique. So we found out there was only one choice for z, 6. And once we knew that there was only one choice for z, plug it into the second equation, we find out that there's only one choice for y, which is determined by that choice for z. So if I know what z is, I can then use that to find out what y is, and there's only one choice. And in the same way, the z that we found and the y that we found, uniquely, the only choices that we had for y and z, determined in turn the only choice that we have for x. And this is a pretty common phenomenon that we're going to find out as we solve more and more linear systems using these kinds of strategies, is that the values that we get for one variable are going to determine the values that we get for the others. Possibly the values for one variable. Sometimes there might be more than one variable which is necessary to determine the values of the others. But that's where we begin to get into the discussion of which variables are what are called basic variables and which variables are called free variables. So I want to close just by making that distinction for ourselves in this example of a linear system so that we'll be able to spot it when we see it later on down the line. To do that, we're going to notice that in the row echelon form of this matrix, once I had zeros all below the diagonal, it turns out that we can identify three special positions in this matrix. I'm going to circle them right here. The entries that are on the diagonal in this example. 1, -15, -27. These entries all have the property that everything to their left and below is all 0. So in the case of the 1, there's nothing to its left, and so that's trivial. But also everything below that 1 is equal to 0. The same is true with my -15. Everything to its left and underneath of it is equal to 0. And for my -27, everything to its left and underneath is all equal to 0. Those three positions are what we call pivot positions. And pivot is maybe the most important concept in the first third of linear algebra. Every entry to the left and below is 0. But the pivot entries themselves, the pivot positions themselves, are non-zero. So once we are in a position where everything below the diagonal has been wiped out, everything below the diagonal is 0, we can identify these pivot positions, the non-zero entries, for which every entry to the left and underneath is equal to 0. And in this particular system, all three columns have pivots in them. Right? So for this system, we're going to say that there were 3 pivots. If we want to be fancy about it, we can say that there were 3 pivot columns. But you might recognize that by the way that I've defined pivot here, every pivot column also corresponds to a pivot row. We can't have one of those without the other. But since the columns in our system correspond to the variables in my original system of linear equations, that means that these pivots actually correspond to variables. Right? This first column here corresponds to x, the second to y, the third to z. And because each of those columns has a pivot in them, that says something about those variables. That because the x column has a pivot in it, the x is what we call a basic variable. It's a variable, because there's a pivot in that column, it's a variable whose value is going to depend on the values of other things in the system. Right? So if we want to summarize this a little bit, we can say that what makes a variable a basic variable, those variables that have pivots in their corresponding columns of the row echelon form of our augmented matrix, what makes it a basic variable is that its value depends on something else. Its value cannot be chosen arbitrarily by the random forces of the universe, but its value is bound to the values of some other thing. Right? So sometimes basic variables are called bound variables or determined variables, but the author of our book calls them basic. And so those are the variables whose value depends on something else. So already looking in this diagram here, because this is our value for z determined y and our values for z and y determined x, that means that y and x are beholden to the value of z. So for sure, x and y are going to be basic variables. Because in order to find their value, we need to first know the value of z. But what about z? Is z a basic variable? Is its value bound to something, or can it be chosen arbitrarily by the forces of the universe or by my personal feeling? And the answer is no. We found out that z had to have the unique value 6 in order for this system to have a solution. And so the value for z is also bound to something, right? It's bound to the stricture of the system itself. And so we can't choose z arbitrarily, and that makes z a basic variable as well. So x, y, and z are all basic variables in this example, because their values are strictly determined for us, that there's no latitude for us or for the forces of the universe to choose different values for x, y, and z, that the values that we got at the end were completely determined by the system that we started with in the beginning. So all of x, y, and z are basic variables in this example. So I want to close by looking at an example, a different example, where that doesn't happen. So let's suppose that I had solved a linear system and I had gotten down to a row echelon form that looks like this. And what makes this different, what might jump out at you right away, is that this is a situation where an entire row of my augmented matrix has gone away. It's become all 0. So I've left it all blank in this example. That would look like, if we translated this back into equation form, one of the equations in my system completely going away and leaving me with the equation 0 on the left-hand side is equal to 0 on the right-hand side. And since all my x's, y's, and z's have vanished from that equation, I get an equation which is always true in this example. 0 is equal to 0, regardless the values that x, y, and z might take. And so this is a very different kind of situation when this happens. Because when I go looking in my augmented matrix, I'm only going to find now 2 pivot positions. I'm going to find the first column has a pivot. This 1 right here has only zeros to its left and underneath. And this 2 in the second row only has zeros to its left and underneath, but those are the only pivots in my system now. And so let's take a look at what happens to the nature of the solution in this example. If I try to use my back substitution strategy, once again, I can't use my third equation to tell me anything about z, because there's no longer a z or indeed any variable in my third equation. So the best I can do is go up to my second equation and try and understand the ways in which my basic variables, and here my basic variables are going to be x and y, those are the ones in the pivot columns anyway. I'm going to try and understand how the values of x and y are determined, are bound, to the value of the other variable, which is apparently not a pivot variable. How are the values of x and y bound to the value of z? To find that out, what I can do, the best I can do, is solve that second equation to get y by itself. If I do that, subtracting z from both sides and then dividing by 2, I'm going to get y is equal to 5 halves minus 1/2 z. And so, as much as I can say at this point is that I don't know yet what value z has, but as soon as z has a value, this is how I can find the value for y that is determined by that z. And in the same way, I can solve this first equation. I can back substitute that y into my first equation. Well, my first equation no longer has a y in it at all, so that's a transparent substitution. But you can imagine if there was a y here, we would have to stuff 5 halves minus 1/2 z in its place. And then rearrange this equation to solve for x. If I do that, I just end up adding 2z to both sides and finding out x is equal to -1 plus 2z. And so we can see from this rearrangement that whatever value z has is going to determine values for x and y, But there's nothing in this solution which tells me that z has a specific value. And so the value of z can be literally anything. And that's what makes z what we call a free variable. That's a variable where there's a free choice. We don't know specifically what values x and y take, but as soon as you tell me what value z has, and I'm relying on you or the forces of the universe or my personal feelings or what I had for breakfast this morning to do so, as soon as we pick a z, that z is going to determine y and it's going to determine x. And that's why we call z a free variable and x and y basic or bound variables. That's an important distinction that we're going to work more with as we get into next week, because it has a huge impact on the nature of the solutions of the systems in which we discover them.